Good afternoon, ladies and gentlemen. This is chapter 2, representing position and orientation. In this chapter, we will look at a way to represent mathematically the position and orientation of an object in two-dimensional and three-dimensional space. Numbers are an important part of mathematics. We use numbers for counting. We use denominate numbers, a number plus a unit, and we call this single number a scalar. So if we have a robot which is 2 meters away, we use a number plus a unit to describe it. We use a vector, a denominate number plus a direction to specify a location. So if you have a robot which is 2 meters away, it's not enough to know exactly the position of the robot because it can be anywhere on a circumference of a circle with 2 meter radius. So we need some sort of information on the direction as well. So we use a vector for that purpose. We may also want to know the orientation of the object. So it's not enough, again, to even to know the position. We also want to know what is the heading of the robot, or where is it facing to. So that is the orientation of the robot or object. So the combination of position and orientation we call pose. A point in space is a familiar concept from mathematics and can be described by a coordinate vector shown in figure 1. So this is a point P described by a coordinate vector with respect to an absolute coordinate frame. So this is the coordinate frame with axis, x-axis and y-axis. These axes are perpendicular to each other, 90 degrees, and the intersection of the axis is called the origin, as you know. And normally a point is represented by a vector, and a vector, you know, can be represented by a line. So the vector represents the displacement of the point with respect to some reference coordinate frame. We call this a bound vector since it cannot be freely moved. So as you know previously, that a vector can be moved around the space, but because we are using a vector to represent a point and this point doesn't move unless you move it, we call it a bound vector. A coordinate frame or Cartesian coordinate system is a set of orthogonal axes which intersect at a point known as the origin. Okay, you know that already. And a vector can be described in terms of its components, a linear combination of unit vectors which are parallel to the axis of the coordinate frame. So you can imagine that, of course, this is the axis. You can imagine there's another vector that we call unit vector whose the length is 1, right? So let's see. So if this is a point, so this is x-axis, y-axis, this is the coordinate frame. If you have a point, and previously you know that a point can be represented by a vector. So if the x coordinate is 3 and the y coordinate is 5, you know P, this P, the point is 3, 5. This is a vector, right? This is 2 by 1 matrix, or we call this a column vector. But what really happens is that we are actually representing P as a linear combination of unit vectors. So there's a unit vector here, x hat, the length is 1, and there's another unit vector here, y hat, again the length is 1, and x hat is really 1, 0 because it does not have y component, and y hat is 0, 1, right? So what is P? P is a vector which is this line, and we know that this vector is this line up to here plus another vector from here to here, right? So what is the vector from here to here is really 3 multiply the unit vector, 3x hat, plus, so P is 3x hat plus 5 of y hat. When we substitute x hat and y hat, we get 3 multiply 1 0 plus 5 multiply 0 1, you get 3 5. So that's how you got the mathematical description of a point that you have known already. So let's move on. Note that points or vectors are different types of mathematical objects, even though each can be described by a tuple of numbers. Right? So points, it can be represented by a vector, but we cannot move a point around. And vector, you know what is a vector? A velocity is a vector, and you know many quantities that are vectors. Right? We can add vectors, but adding points makes no sense. The difference of 2 points is a vector, and we can add a vector to a point to obtain another point. So a real object comprises infinitely many points. So imagine if you have a mobile robot, there are many points on that robot, and an object, unlike a point, also has an orientation. So imagine your robot either facing you or facing left or facing right, because a robot has a sense of which part is the front and which part is the rear or the back. So it has orientation when you place it somewhere and rotate it. So if we attach a coordinate frame to an object as shown in figure 2, so imagine this is your mobile robot. This is the coordinate frame. It can be a reference coordinate frame, and as we will see later, this is also known as the world coordinate frame, which does not move. And attached to our object, in this case a mobile robot, is we have this body attached coordinate frame. So this coordinate frame, xb and yb, it is fixed on the robot, and whenever it moves together with the robot, it's fixed. So you can imagine if you have a point here, so this point is always fixed with respect to coordinate frame b. So the points are described with respect to object's coordinate frame b, which in turn is described by relative pose psi b. Axes are denoted by thick lines and so on. So let's go back here. So now we can describe the position and orientation, or we call the pose, of that coordinate frame with respect to the reference coordinate frame. So because we have attached our coordinate frame fixed on the robot, so the position and orientation of our mobile robot is just the position and orientation of our coordinate frame with respect to this reference coordinate frame. So to distinguish the different frames, we label them, and in this case the object coordinate frame is labeled B in curly brackets, and its axes are labeled xb and yb. So we always label our coordinate frame in this form. So in this case this is B, and we use curly brackets to represent our coordinate frame. Okay. And so this is a Greek letter which we pronounce as xi, and xi b means the pose of coordinate frame b with respect to this coordinate frame. So often we would write it in this way. So normally we will write psi BO or BA, depends on which coordinate frame we are referring to. In this case, we are describing psi is the pose. Note that pose is position and orientation. So psi is pose of B with respect to this coordinate frame. So if it has no leading superscript, that means it's understood this is a reference coordinate frame, and normally reference coordinate frame we label as O, right? The world coordinate frame or the reference coordinate frame we label as O. So you should know in the future if there's no leading superscript here, so psi B is actually Kasai BO. Right. So to completely describe the pose of a rigid body in a three-dimensional world, we need 6 and not 3 dimensions. 3 to describe its position, x, y, z, and 3 to describe its orientation. And these dimensions behave quite differently. If we increase the value of one of the position dimensions, the object will move continuously in a straight line. So imagine if I move the origin of coordinate frame B in x direction with respect to the world coordinate frame, so this mobile robot will be moving in a straight line, right? If we move it in the x direction. However, if we increase the value of one of the orientation dimensions, the object will rotate in some way and soon get back to its original orientation. Therefore, we say this dimension is curved. So what does that mean, right? So if I rotate my mobile robot around xb, so you can imagine we rotate this around xb, right? So when we have rotated it 360 degrees, it will get back to the original orientation. So the dimension is therefore curved. On the other hand, if I increase the value in the position dimension, right, in x-axis, it will continue to move. But if I rotate it in the orientation dimension, it will get back to the same orientation after some time. So the pose of a coordinate frame is denoted by the symbol Kasai. So figure 3 shows two frames, A and B, and the relative pose Kasai BA, which describes B with respect to A. So this is frame A, and these are the axes, YA, XA, and this is coordinate frame B. So Kasai BA is the pose or the position and orientation of frame B with respect to frame A. So note the superscript and the subscript. So subscript refers to the coordinate frame that we are trying to describe, and the leading superscript refers to the reference. What are we referring to? So we have a point here, right? So this point can be different vector depending on which coordinate frame we are referring to, right? So if we want to describe this point with respect to coordinate frame A, we use this symbol PA, and the same point if we want to describe with respect to coordinate frame B, we use this symbol PB. So the point P can be described by coordinate vectors relative to either frame A or frame B. The pose B relative to A is Kasai BA. So I've explained this. So we can also think of Kasai BA as describing some motion. Imagine picking up A and applying a displacement and a rotation so that it is transformed to B. So one way of looking at this Kasai BA is just the position and orientation of a coordinate frame with respect to another, right? In this case, B with respect to A. But you know that how do we get B? So you can imagine in the beginning, it was not like this, but it was like this, right? So imagine in the beginning, A and B is parallel like this. You can see the green axis here, green coordinate frame. So first step, we move it, we translate it to this point. We have this coordinate frame now. And the second step, we rotate it theta. We rotate it by theta and you get the B coordinate frame. So in a way, it's a motion, right? So we started here, the green one, we move here in parallel. So everything is parallel. And when we get here, we rotate by theta. So what is PA? As I said earlier, PA is the mathematical description of point P, right? So So that means we are looking at this coordinate frame and we are trying to get the coordinate of P. So maybe PA can be 3, 5, right? So what is the x coordinate? So maybe this is 3, the y coordinate can be 5. But the same point, if we describe it mathematically with respect to coordinate frame B, it can be minus 2, 1, because P is around here along the xb, so it's minus 2 maybe, and perhaps is positive 1 here along yb, so therefore it's minus 2, 1. Okay, so the point in figure 3, this is figure 3, can be described with respect to either coordinate frame by the vectors PA or PB respectively. Formally, they are related by this equation. So PA equals to psi BA. We have an operator here which we have not defined, operator PB. So what it means is that, so we want in the future, because when it comes to robotics and many other fields, we would be changing the description of a point or a vector or a pose from one frame to another. So we want to have a way to change, to transform a point from one frame to another. So what happens here is that we are transforming the point PB to PA. So if you want to transform the point from coordinate frame B to A, so this would be it. So note that we have not described, we have not determined what is psi BA. For now, it's just a label of position, orientation, or pose. And again, this operator we have not defined yet, but we want to find out. An important characteristic of relative poses is that they can be composed or compounded. In figure 4, if one frame can be described in terms of another by a relative pose, then they can be applied sequentially. So let's see figure 4. This is figure 4, a point P which can be described by coordinate vectors relative to either frame A, B, or C. The frames are described by relative poses. So here we have 3 coordinate frames: coordinate frame A, coordinate frame B, and coordinate frame C. So coordinate frame C with respect to the pose of C with respect to B is given by the label psi CB. So the arrow here is just a representation of the pose. So don't get confused by thinking that this could be a position or orientation. This is both. The arrow here representing the pose, position, and orientation. And the pose of coordinate frame B with respect to A is labeled as psi BA. So now we have point P. So once again, we can describe P with respect to A, PA, or B, or even C, PC, and that would result in different vectors. So we want to be able to get new pose from existing poses. So if I have psi BA and psi CB, if I have psi BA and psi CB, and I'm interested in finding psi CA, which means the pose of this with respect to pose of this. So I can actually do this: psi BA composed with psi CB. So which says in words that the pose of C relative to A can be obtained by compounding the relative poses from A to B and B to C. We use this operator to indicate composition of relative poses. So we have not, once again, defined what is this operator. But in this chapter, we will look at what is exactly this operator, such that given existing poses, we can compound them or compose them in order to obtain another pose. And when you have that, you can actually find PA from PC. So if you noticed, in order for these operators to work, the subscript and the next leading superscript has to be the same, right? This is B, and therefore you can compose BA and CB. And here the subscript is equivalent to, is the same as the leading superscript, and therefore you can perform this operator. So we will see in the future what is exactly this object mathematically and what are these operators. So in these examples, so far we have shown two-dimensional coordinate frame, and this is appropriate for a large class of robotic systems, particularly for mobile robots which operate in a planar world. But for problems like maybe robot arm, drone, and so on, we require three-dimensional coordinate frame. It's because to describe objects in our three-dimensional world, such as the pose of a flying or underwater robot, or the end of a tool carried by a robot arm, we need three-dimensional coordinate frame. So because this is still introduction, so far we have only seen two-dimensional coordinate frames. And figure 5 shows a more complex three-dimensional example in a graphical form, where we have attached 3D coordinate frames to the various entities and indicated some relative poses. So now here is the multiple three-dimensional coordinate frame and relative poses. So similarly, if you have three-dimensional coordinate frames, the position and orientation is labeled as psi, and because it's always relative, it's either relative to the world coordinate frame or relative to other coordinate frame, we have superscript and leading, we have subscript and leading superscript. So psi BC is the pose of B with respect to C, right, and so on. So let's see what's happening here. So the fixed camera observes the object from its fixed viewpoint and estimates the object's pose psi BF relative to itself, right? So there's a fixed camera, we have fixed world coordinate frame, we have a robot that is moving, we have a camera on robot, which means so whenever a robot moves, this moves as well, right? So psi CR is always constant, it doesn't change, assuming the camera does not turn, right? But it's fixed on the robot. And the other camera is not fixed. This camera is not fixed. This is fixed with respect to the world coordinate frame. It is attached to the robot, the other camera, at some constant relative pose and estimates the object's pose psi BC relative to itself. So this camera will obtain the pose of the object with respect to itself and the robot. Recalling that we can compose relative poses using this operator, we can write some spatial relationships. So psi F composed with psi BF is psi F composed with psi BF is really the pose of B with respect to O, and that is equivalent to psi R composed with psi CR composed with psi BF. So it's equivalent to psi R composed with CR composed with BC. So one way of looking at this is, because we are getting the pose of B with respect to O, which is this one, you can see that this vector is really this plus this, right? Of course, when it comes to pose, we don't use plus, we use a compositional operator, which we will define later. And and this is also this plus this plus this. So that is if you want to look at the arrows. But a more concrete way is by looking at the, as I said earlier, the subscript and the leading superscript of the next pose. So if they are the same, then you can do the composition. Okay, and here we get Kasai R. What is Kasai R? This is Kasai R. So this is really F and FR. So there's no FR here. So RF is the pose of robot R with respect to the fixed camera. Okay, so by composing Kasai F and Kasai RF, you would get Kasai RO. Okay, now let's look at working in 2 dimensions. So we use a right-handed Cartesian coordinate frame with orthogonal axes denoted x and y. I have explained this earlier. Origin, I've explained. Unit vectors, I've explained. A point is represented by this way, I've explained as well. Figure 6, this is figure 6, shows a red coordinate frame B. This is red coordinate frame B that we wish to describe with respect to the blue coordinate frame. So how do we describe the position and orientation, also known as pose, of B with respect to A? So as we will see later, the position of B is just the position of the origin with respect to A. And the orientation is how much it has rotated with respect to A. We can clearly see that the origin of B has been displaced by the vector t, and the components are x and y, and then rotated counterclockwise by an angle theta. So I've explained this earlier. So you can imagine in the beginning, the red coordinate frame was not here, but it was here, right, in parallel to the A coordinate frame. So the first step, we move it to this point by t without rotating, and the second step, we rotate it by theta, and that results the coordinate frame B. So consider an arbitrary point P which we can express with respect to each of the coordinate frames shown in 6. So we have point P, and you know that so P can be described with respect to, so we are referring to figure 6. So this is figure 6, all right? So consider arbitrary point P. So this is point P, this is figure 6, right? Okay, so if you want to describe, so P can be described with respect to the B coordinate frame, right? PB, we call it PB, as shown by this arrow. And the components will be XB and YB, right? So imagine there is if the X component, we call it XB, and the Y component, we call it YB. And if we describe the same point with respect to V, or we haven't talked about V yet, so let's go through the next point. So we create a new frame V whose axes are parallel to those of A, but whose origin is the same as B. So see figure 7. So now we are talking about figure 7. So figure 7 refers to figure 6. So this is figure 6 without the green coordinate frame, and we have an additional coordinate frame V. So V is new frame, axes are parallel to A, but origin is the same as B. Okay, so we establish a new coordinate frame. The axis is parallel to A, right? But the origin coincides with B. So we have this green, the green coordinate frame, or this one, okay? And looking at P, so now we can talk about this. Looking at P, we know that if we describe P with respect to B, we have XB, YB. If we describe P with respect to V, we have Vx, Vy. Okay. And using trigonometry, you can establish that x hat b, right, the unit vector of this is really cos theta sine theta, and y hat b, the unit vector of this, is minus sine theta cos theta. So how is this useful for us? So according to equation 2, which we have seen earlier, point P, we can represent it by this way, right? So a point is a linear combination of the unit vectors. So xv, x hat v plus yv, y hat v, and you can factor this in terms of a row vector and column vector, so which we have written as a product of row and column vector, all right? And coordinate frame B, as I've said earlier, is really cos theta x hat v plus sine theta y hat v, and the same is y hat b. Okay, and this can be factorized into matrix form as this one. Okay, so from here we get this, and the same thing with point B, sorry, PB, we can describe in this way. Because we have a description for the unit vector of x hat b and y hat b, if we substitute this in here, we will get this. Okay, so this is another description of PV. So earlier we have PV, and now we have another PV. So comparing the two, we can see that this part here, xv yv, is this whole thing. Okay, so xv yv is equivalent to this. So what we have done here basically is that we have transformed a point from B coordinate frame to coordinate frame V. So xb, what? xb, xv, right? So go back to the figure. So we have transformed this point, which is the description of point P with respect to B, we have transformed it to PV. So PB to PV. Okay, so this describes how points are transformed from frame B to frame V when the frame is rotated. So this type of matrix is known as rotation matrix, since it transforms a point from frame V to B and is denoted RBV. So now we rewrite this as this. So RBV is our rotation matrix. So this means that we are representing the rotation of a coordinate frame B with respect to coordinate frame V. And if we want to transform a point from one coordinate frame to another, in this case we can transform PB to PV, right? We can transform PB to PV. So we can rearrange equation 6. So of course from here we can obtain PV given PB. What if I want to compute PB? So note that this is so this is so we can rearrange equation 6. So now this is equivalent to the inverse of the rotation matrix. And rotation matrix is a special matrix because if you compute the inverse of this, is really the transpose of the matrix. So that makes things a bit easier. And you know, transpose, column becomes row and row becomes column, right? And a transpose or the inverse is really switching or swapping the superscript and the subscript. Okay, so this really becomes RVB. Note that inverting the matrix is the same as swapping the superscript and subscript which leads to the identity R minus theta equals to R theta transpose. So we will look at some examples later. So for now, you have to know that we have established the rotation, the representation of a rotation of a two-dimensional coordinate frame with respect to another coordinate frame. So this is the rotation matrix that we saw earlier. So it's a special two-dimensional rotation matrix with some special properties. It is orthonormal or orthogonal, which means the columns are unit vector. So this is a unit vector and this is a unit vector, and the columns are orthogonal. It is perpendicular to each other. And you have to know that this rotation matrix represents the rotation of, or the orientation of coordinate frame y with respect to coordinate frame x. So this is how it looks like, right? And each column, so this column represents x hat y with respect to coordinate frame x. So therefore the x component is cos theta and the y component is sine theta. And this column represents y hat y with respect to coordinate frame x. So therefore the x component is minus sine theta and the y component is cos theta. So the columns are the unit vectors that define the axis of the rotated frame y with respect to x, and by definition both unit length and orthogonal. And the inverse is the same as the transpose. So that's always the case when it comes to rotation matrix. So So we have described the orientation or the rotation in 2 dimensions. Now let's move on to pose, kasai. So remember or recall, pose is position and orientation. Now we need to account for translation between the origins of the frames shown in figure 6. Since the axes V and A are parallel, as shown in figures 6 and 7, this is simply vectorial addition. So what is happening here? So if you remember, this is PA. Let me try to write this here. Oh, I think it becomes smaller, so it's not convenient. Let me try it anyway. Alright, so yeah, so recall that this is PA, right? The description of the point with respect to coordinate frame A, and this is PV, and this is T, the vector. Okay, so let me try to close this. Alright, so this point with respect to A, so you can imagine this is the vector. So this vector is T, this vector, plus this vector. But this is PB. Here we use PV, right? So the vector should be the same, right? But no, the line is the same, but the vector is different, right? The numbers are different. So we have previously defined or derived PV like this. So if you scroll up, you will see this, and from here to put in a different form, we get this form. So you can already see that PB, this is PB, right? XB, YB. We have added the number 1 here, the element 1. So previously it is 2 by 1, now becomes 3 by 1, right? 3 by 1. So rewriting this, we get this form. So again, PA has become this object here with an addition element 1. So this is what we call the homogeneous coordinates, a homogeneous form. And this matrix now contains the rotation matrix, which represents the orientation, and it also has T. T represents the position. If you recall earlier, I said the position of a coordinate frame is just the position of the origin of the coordinate frame with respect to another coordinate frame. So now this matrix represents both position and orientation of coordinate frame B with respect B with respect to A. So this will be a 3 by 3 matrix, and the last row is always 0, 0, 1. So note that RBA is the same as RBV, since the axes of frames A and B are parallel. So the rotation matrix of, so let's look at this. So the rotation matrix of B with respect to V is the same as RBA, because the coordinate frames A and V, they are parallel. Okay, so rotation is just angles, right? It depends on the orientation. So we are trying, because we are trying to represent the unit vector with respect to a coordinate frame. So if two frames are parallel, and the orientation is the same. So the coordinate vectors for point P are now expressed in homogeneous form, and we write this way. Okay, so instead of PA, we have P tilde A. So we have more symbols. Right, so P tilde A is homogeneous coordinates. So because we are still talking about 2 dimensions, and P tilde A is no more 2 by 1, it's 3 by 1, because we have added 1 here. And this matrix, we label it as TBA, and this is what we call the homogeneous transformation or homogeneous matrix. So now we have pretty much described the position and orientation as we desired. So remember earlier we used the notation Kasai, right? Kasai BA. So now, because Kasai BA is just a label, and now we have actually determined what is really Kasai BA. So Kasai BA is really TBA, this 3 by 3 matrix. So a vector P is written in homogeneous form. In our case, x3 is always 1. The dimension has increased by 1, and a point on a plane is now described by a 3 vector. To convert a point to homogeneous form, we typically append an element equal to 1. So we just add 1 and P becomes P tilde. So the tilde indicates the vector is homogeneous. So by comparison with equation 1, it is clear that TBA represents translation and orientation of relative pose. This is often referred to as a rigid body motion. So now this is our Cassini, right? A concrete representation of relative pose is T, right? Is given by this. And if previously we used this, we said that we could compose 2 poses, but we have not determined what is the composition operator, and it turns out to be that it's just multiplication, right? So if you have TBA so if you have if you want to know what is TCA, so this is the pose of coordinate frame C with respect to coordinate frame A. And if you know TBA, and if you know TCB, you can just multiply them together, right, as given by this. So TBA multiply TCB, you would get TCA. So when you multiply or you compose 2 poses, just make sure the subscript is equivalent to the leading superscript, which is a standard matrix multiplication. Because you have calculators that can perform 3 by 3 multiplication, you can just do it. But because this is a special matrix, when you multiply the two homogeneous matrix, this is how it behaves. So this is so the resultant matrix is always R1 multiplied R2, and this part, the last column is always T1 plus R1 T2. So maybe you can use this as a way to check whether your answer is correct or not. And the inverse, once again, you can do the inverse by using a calculator, but as a way to check, the inverse is just this part. The 2 by 2 component here is just the transpose of the rotational matrix, and the last column is just this, and the last row is always 0, 0, 1. When it comes to homogeneous matrix, the last row is always 0, 0, 1, no matter what you do. Now let's look at some examples. So we are given two coordinate frames here. One is the coordinate frame V, Vietnam, which is shown in green, and the other one is coordinate frame B, which is shown in blue. We're also given a point here, point P, and without even mentioning here, we know that from observation, PV, which means the point with respect to the green coordinate frame, is 0, 1, because the Y component is 1 and there's no X component. And PB, point P with respect to the blue coordinate frame, is 1, 0. And what is the rotation matrix RBV? In other words, what is the representation of the rotation of coordinate frame B, Bangkok, with respect to V, is given by this formula, by this matrix, and theta is the angle. Because coordinate frame B has been rotated this way, it seems to be anti-clockwise, therefore it's 90 degrees. If it has been rotated clockwise, it has to be minus 90 degrees. So there's a perfect explanation why the direction is such, as we will see in the 3-dimension case later. So theta is 90 degrees because we have rotated B from V this way. So cos 90 is 0, sine 90 is 1, therefore it's minus 1, 1, and again it's 0 here. So even without this, using this formula, you should be able to derive this matrix, because it says here the columns are the unit vectors that define the axis of the rotated frame Y with respect to X. So this column is the unit vector of XB with respect to the green coordinate frame V. So if you see, what is the coordinate vector XB, which is this, if you imagine there's a coordinate unit vector here. What is the unit vector here with respect to coordinate frame V? It is indeed 0, 1, because there is no component here. So it's pointing this way, upwards. And what is the unit vector YB, which is pointing this way with respect to coordinate frame V? It is minus 1, 0. So as you can see, you can either use this formula with the correct theta, rotation angle, or you can just describe by observation. So each column, as said here, are the unit vectors that define the axis of the rotated frame. Alright, so suppose we are interested to find PV, even though we know already, but let's say we want to find it. Or let's test what we have learned so far. So what is PV with respect, if we are given the rotation matrix and PB? So as we saw here, so it's just the multiplication. So RBV multiplied PV, PB, we know is 1, 0, we get 0, 1, which is correct, as we observed earlier. All right. Suppose we are interested to find PB now. Given PV, first we have to find RVB. So note that previously we used RBV. Now the superscript and the subscript is reversed. So once again, you can find RVB either by using this formula or, like I said, by observing. So we are interested to find RVB. So let's look at XV. So what is the unit vector of XV, which is pointing this way with respect to coordinate frame B? It is 0, minus 1. So let's say it is 0, minus 1. What is the unit vector of YV, which is pointing upwards with respect to coordinate frame B? It is 1, 0. 1, 0. If you still want to use the formula, no problem, but be careful of the angle. So V is pointing, coordinate frame V is this way. So it has been rotated from coordinate frame B this way, 90 degrees, this way, which is clockwise. Therefore, we have to use minus 90 degrees, as shown here, cos minus 90, minus sine minus 90, and so on. So this is the matrix. So that is one way to find RVB. Because we have computed RBV, we can just transpose it to get RVB. There's a mistake here somewhere. Okay, this should be RBV. Let me correct this quickly. Apologize for this. So this should be RBV. So RBV, which we have computed earlier, transpose of it is RVB. So it is given here, right? The inverse, no, I think it's given here, right? If you transpose a rotation matrix, it's like swapping. What you're doing is you're swapping the superscript and the subscript. So RBV, which is this one, transpose, you get RVB. So what is RBV is this one, 0, 1, minus 1, 0. Transpose, as you know, transpose is column becomes row, row becomes column. So 0, 1 becomes here, 1, 0 becomes here. Okay. Now what is, so as you can see, using method 1 and method 2, we get the same matrix, therefore it's correct. So what is PB now? So RVB multiply PV, which is 0, 1, and the answer is 1, 0. Is it correct? Let's check from observation. Yes, it is correct. Okay, let's move to the so maybe I should explain another thing here. This way, this one, which leads to the identity R minus theta equals to R theta transpose. So indeed, as we see here, this is minus theta, and this is R minus theta, and this is R theta transpose. Okay, so this is we transpose R 90 degrees, right? We get this. And this one, what is this one is that the rotation with minus theta, 90 degrees, but it's minus. So it is equivalent. So this statement is correct. Let's look at the pose now. So we have come up with this, right? So the pose, which represents the rotation and orientation of a coordinate frame or an object, is given by this, right? So the last row is always 0, 0, 1. And the top left 2 by 2 matrix is just the rotation matrix that we have seen earlier, this one. And this is a 2 by 1 vector representing the position of the origin of a frame, in this case of frame B with respect to frame A. And also note that the coordinate of a point has to be represented in a homogeneous form. Okay, so we are given again two coordinate frames, coordinate frame V, Vietnam, and coordinate frame B, Bangkok. And we have a point here. As you can see, the point with respect to coordinate frame V is 0, 2, right? But the same point with respect to coordinate frame B is 1, 0. So now we are just trying to test out the homogeneous transformation matrix that we have learned. So suppose the question is compute PV given PB. So later when we get the answer, again we want to check with this. If it's correct, then what we have learned is correct. Alright, the first method is by just adopting this matrix. So TBV is given by this. First of all, let's look at the rotation. What is the rotation of B with respect to V? As we can see, we have rotated 90 degrees. So even though the origin is not the same as we have learned earlier, this statement here, right? Note that RBA equals to RBV since the axes of frames A and V are parallel. So when it comes to rotation, it doesn't matter where is it, but you just refer to the coordinate axis. So, or you can imagine there's another coordinate frame here, right, with the same origin, and this is X and here is Y, right, which means this X is parallel with this and the Y is parallel with this. So if you imagine there's a coordinate frame here, X and Y, so it's clear that coordinate frame B has been rotated 90 degrees. Because it has been rotated 90 degrees, we apply this formula, this matrix, we plug in 90, theta equals to 90. So as you can see, cos, C for cos and S for sine for short form, shorthand notation. So we get this matrix, okay? And remember that T is, what is T? T is the position of this origin with respect to coordinate frame V. Now the position of this origin is 0, 1. So we plug in here 0, 1. And the last row is always 0, 0, 1. So this is our homogeneous transformation matrix TBV. So next we can just compute P tilde V, which is TBV multiply P tilde B. So P tilde B is exactly this one, but we have to append or add 1 here to make it 3 by 1 vector. So 1, 0, 1. And if you perform the multiplication, we get 0, 2, 1. So this is not the coordinate, this is the homogeneous coordinate. So we have to extract the first two elements here, 0, 2. So that is our PV. Let's check. Yes, it's correct. That is one method. Another method is by looking at this as a series of motion, a series of rotation and translation. So we know that this is what we have. This is our problem. So imagine in the beginning, you have an imaginary coordinate frame V prime shown as this, which is parallel, which coincides with our coordinate frame V. So origin is the same, xv prime pointing in the same direction as xv, yv prime pointing the same direction as, which is parallel with yv. So we are going to perform a series of rotations, appropriate rotations and translations, in order to arrive at coordinate frame B. So how do we do that? First we have here. Secondly, we translate this to this point, and we have a new coordinate frame, another imaginary one, V double prime. So you can imagine, you can see it's parallel, but now the origin is translated to this point. So what is T V double prime V? What is the position and orientation of this coordinate frame with respect to this coordinate frame? So as we know, the rotations, this is rotation part. There's no rotation, right? Because it's parallel. XV double prime is parallel with XV prime, and YV double prime is parallel with YV prime. So the angle is 0 because there's no rotation. So remember, this one is the rotation matrix, cos 0 minus sin 0, sin 0, cos 0. And the last row is always 0, 0, 1. So what is the origin of V prime, V double prime with respect to V prime? It is 0, 1. So 0, 1. So next motion is, so from here we rotate this way, which is positive 90 degrees to arrive at our coordinate frame B. And we have to obtain its homogeneous transformation matrix TBV double prime. The rotation, the angle is 90 degrees, but there's no translation. The origin remains the same as this one, so it's 0, 0. Next, if you refer to this point here, it says that we can compose a series of relative poses by just multiplying its respective homogeneous transformation matrix. So we are interested to find TBV, right? The original problem, we are interested to find TVB. So TVB, you multiply TV double prime V with TB V double prime. So you have to make sure, as I've said earlier, the subscript and the leading superscript is the same. Only then you can perform multiplication. So this multiply this, you get this, which is it the same as our first approach? Indeed, it is the same. 0, 1, 0, minus 1, 0, 0. 0, 1, 0, minus 1, 0, 0. 0, 1, 0, 1 is correct. Okay. Now, what if I want to find PB? Right, in this first problem, we want to compute PV. What if I want to now compute PB? So PB, right? So P tilde B tilde, because we have to represent it in a homogeneous transformation, a homogeneous coordinate. But now we have to use TVB. Okay, so multiply P tilde V. So once again, either you can derive TVB by just looking at this, right? Because we know that the column, this column represents the X coordinate frame. Let's try to derive it by observation, if we are good enough, right? So what is what are we trying to find? In the next problem, we are trying to find TVB, right? What is TVB? So what is x-axis with respect to, what is xv, or the unit vector of xv with respect to coordinate frame B? If you notice, it is 0, minus 1, 0, because it is pointing in the negative direction of y. So therefore it's 0, minus 1, 0. And it doesn't matter if the origin coincide or not, because you have to imagine it coincides. And we know the last row is always 0, 0, 0, 1. And what is y-axis? What is y, the unit vector of yv with respect to coordinate frame B? It is pointing in the x direction of B. So it is 1, 0, 0. Sorry, this is oops. Now I'm erasing everything. Let me just do this. All right. So let me repeat. What is x? This x with respect to the B coordinate frame. It is 0, 1, 0 minus 1, 0 minus 1 because x is in the negative direction of y. Okay, and the last row is always 0, 0, 1. So what is yv, or the unit vector of yv with respect to the B coordinate frame? It is 1, 0. So what is the origin of v with respect to B? It is what? 0, 1. So that's how you derive it. Let's check. Did we get it correctly? Oh, no. Because so this is 0, minus 1, 0, 0, 1. This is 1, 0. And the origin is below the origin, right, of B. So this is minus 1. Minus 1. So it's minus 1, 0. Okay. Anyway, if you're not confident with that, so as you can see, 0 minus 1, 0. 0 minus 1, 0. 1, 0, 0. Minus 1, 0, 1. Minus 1, 0, 1. Okay. So, or we can just apply this formula. So because we are interested in computing TVB, and we have computed TBV, right? We have this, so we might just invert it, right? So the inverse of TBV is equivalent to TVB, and you can just use your calculator to inverse it, or you can use this property over here. So this 2 by 2, the last row is always 0, 0, 1. The 2 by 2 here is the transpose of the 2 by 2 here. So 0, 1 becomes 0, 1 here. Minus 1, 0 becomes minus 1, 0 here. And this part is minus R transpose multiply 0, 1. So we take this one, minus it, multiply 0, 1, we get minus 1, 0. So this is our homogeneous transformation TVB. So TVB multiply P tilde V, we get 1, 0, 1. So therefore PB is 1, 0. Is it correct? PB is 1, 0. Okay, let's move on to the three-dimensional case. Working in 3 dimensions. The three-dimensional case is an extension of the two-dimensional case discussed previously. We add an extra coordinate axis, typically denoted by Z, that is orthogonal or 90 degrees to both the x and y axis. The direction of the x-axis obeys the right-hand rule and forms a right-handed coordinate frame. So this is how the two-dimensional coordinate frame would be like. So if this is your x and this is your y, your z always points in this direction as given by your right fingers. So your thumb is x, this finger is y, and the middle finger is z. Or mathematically, z is a cross product between x and y. So if you have your eyes here and you're looking in the positive direction of z-axis, and if you rotate a screw in the clockwise direction, which means from x to y, clockwise, the screw will move in the z direction. And similarly, if your eyes are here and if you're looking in the positive direction of the y-axis, if you rotate a screw in a clockwise direction, rotation from z to x, the screw will move in the y direction. Or if that's too confusing for you, you just use your right hand fingers. So point P is represented similarly as before, as this. And figure 8 shows a red coordinate frame B that we wish to describe with respect to the blue reference frame A. So we have these coordinate frames, B, which is in red, and A, which is in blue. As we can see, the origin of B is displaced from A by this vector T. And T has its x, y, z component now. So x, y, and z. And you can also see that the coordinate frame has been rotated. So maybe from here we rotate a certain angle about x-axis and then again a certain angle about y-axis, and you arrive in this orientation. And you can see a point here. A point can be described with respect to the B coordinate frame or coordinate frame A. So I've explained this. And our approach is again to consider an arbitrary point P with respect to each of the coordinate frames and to determine the relationship between PA and PB as before. So figure 8 shows a pair of right-handed coordinate frames with very different orientations, as you can see, and it's not obvious how we can derive this from here. And we would like to find some way to describe the orientation of one with respect to the other. We can imagine, like I said earlier in the two-dimensional case, picking up frame A in our hand from here and rotating it until it looked just like frame B. So either you pick this one or you imagine there's a coordinate frame V for Vietnam, which completely coincides with coordinate frame A, which means XV is here, YV is here, and ZV is here. And how do you get to here from here? So we'll be using that information. So Euler's rotation theorem states that any rotation can be considered as a sequence of rotations about different coordinate axes. So according to the Euler's rotation theorem, you can absolutely obtain this by rotating this through a series of rotations about different coordinate axes. So maybe first you rotate about Z about a certain angle, and then you rotate a certain angle about Y, and then finally you end up here. We start by considering rotation about a single coordinate axis. Figure 9 shows a right-handed coordinate frame, and that same frame after it has been rotated by various angles about different coordinate axes. So this is figure 9, and we have the original coordinate frame here. If we rotate this coordinate frame about its x-axis 90 degrees, you'll end up here. So it is appropriate now to discuss what is positive angle and negative angle or rotation. So once again, if we want to rotate about x-axis, imagine you have your eyes here and you're looking in the positive direction of the x-axis. That means you're looking this way. So clockwise rotation is positive and counterclockwise rotation is negative. Because this is clockwise 90 degrees, so Z becomes here and Y becomes here, and X of course does not change. What if I want to rotate 180 degrees about X? Again, you're looking at this way from here to here. Clockwise is positive, so Y if you rotate 180 degrees, Y comes here, right? That's why we have this, and Z comes down here. If we rotate minus 90 about X, Z goes here. If we rotate 90 degrees about Y-axis, so you have to look through this direction, and Z will go here, ZX. And positive 90 about Z, that means you have your eyes here, you look in this direction, 90 degrees, so Z goes here and Y goes here. The issue of rotation has some subtleties which are illustrated in figure 10. This shows a sequence of two rotations applied in different orders. We see the final orientation depends on the order in which the rotations are applied. In 3 dimensions, rotation is not commutative. The order in which rotations are applied makes a difference to the results. Figure 10. So let's see two scenarios here. Here first we rotate positive 90 with respect about X. We end up positive 90, that means Y goes up here, right? We end up here, and then next in sequence we rotate 90 degrees about Y, so Z goes here, right? So we end up with this coordinate frame. What if I reverse the sequence, which means I rotate 90 degrees about Y first, and then I rotate 90 degrees about X? So this is what happens. So if we rotate 90 degrees, so you can see that the both of the original coordinate frames are the same. If I rotate 90 degrees about Y, Z goes here. And then if I rotate 90 degrees about X, positive, Z goes here and Y goes here. And the resultant coordinate frames are different. So the point here is that the sequence of rotations play a role, and they might result in different orientations. So you have to take note of that. Mathematicians have developed many ways to represent rotation. So you can use either orthonormal rotation matrices, which we will cover in our course, Euler and Cardan angles, rotation axis and angle, exponential coordinates, and unit quaternions. Just as for the two-dimensional case, we can represent the orientation as a coordinate frame by its unit vectors expressed in terms of the referent coordinate frame. Each unit vector has 3 elements, and they form the columns of a 3 by 3 orthonormal matrix RBA. So if for the two-dimensional case, our rotation matrix is 2 by 2, for three-dimensional case now, our rotation matrix is 3 by 3, which transforms the description of a vector defined with respect to B to the vector with respect to A. So this matrix is the same as before, except that now the dimensions are different. So our three-dimensional rotation matrix has some properties similar as before. It is orthonormal. The columns are the unit vectors that define the axis of the rotated frame Y with respect to X. and the inverse is the transpose. The difference now is that we have 3 rotational metrics, because previously you can only rotate parallel to the plane, to the two-dimensional space, even though there is no z-axis in two-dimensional space, because it would be meaningless to bring in the notion of z-axis. But looking from a 3D perspective, z is there, right? So that's why we did not mention z-axis when we discussed the two-dimensional case. So now, if we are working on in three-dimensional space, you can rotate a coordinate frame with respect to x, about y, or about z, or all three in sequence. So if we rotate a coordinate frame with respect to x, this is the rotation matrix. Y, this is the rotation matrix. RZ, this is the rotation matrix. So as you can see, they are all different. So that was orientation, or the rotation. Now let's look at pose. So the position and orientation change between two coordinate frames, often known as rigid body displacement or rigid body motion. Because even in the two-dimensional case, we saw that in order to describe the pose of a coordinate frame, we can imagine moving that coordinate frame from the reference coordinate frame through a series of translation and rotation to arrive at the coordinate frame of interest. The derivation for the homogeneous transformation matrix is similar to the previous 2D case, but extended to account for z dimension. So this is how it looks like. As you can see, it's similar, except that this is now 4 by 1. This is 3 by 3 instead of 2 by 2. This is 3 by 1, and the last row is 0, 0, 0, 1. So this matrix, the homogeneous transformation matrix, is now 4 by 4. It's not 3 by 3 anymore. In two-dimensional case, the homogeneous transformation matrix is 3 by 3 matrix. And this is how you map a point from one coordinate frame to another. In this case, from B to P, you have to represent the coordinate in its homogeneous form. And once again, these properties apply as before. So if you multiply the two, there should be an equal sign here. So if you multiply these two, you will get this. Or you can just use your calculator to multiply a number of 4 by 4 matrices. So you can disregard this. Well, the inverse part, again, you can use your calculator, or you can apply these properties. All right, let's look at some examples to make your understanding better, or to give you any form of understanding. All right, let's start with this one. So we have two coordinate axes here, coordinate frame A, which I have not labeled for clarity, but you know this is XA, so this is the coordinate frame is coordinate frame A, and this is coordinate frame B, and we have a point. And in this case, the point is given, but with respect to B, 0, 1, 0. So that means it is on the YB equals to 1. Our task here is to find what is P with respect to A. So what is this point with respect to this coordinate frame? From observation, you can clearly see that it has the X component, or XA component, is -1, and the YA component is 3, and the ZA component is 0. So this is useful because we can compare our answer obtained through calculation with this and check whether it's correct or not. So there are various ways to do this. I mean to obtain the TBA. So obviously if you want to compute PA, we have to compute we are interested in computing PA. So if you want to do this mathematically, then we have to compute TBA multiply P tilde of B, because this is given. So we have to compute this. And you know that this can be derived by looking at this two coordinate frames, because we know that the top 3 by 3 is rotation matrix, and rotation matrix, by definition, the columns are the unit vectors that define the axis of the rotated frame. Okay, let's try to derive this. So let me write here, right? So what is TBA by observation? If you are expert in this, someday you can do this. So the last row is always 0, 0, 0, 1. T, as before, it is the position of this origin with respect to coordinate frame A. What is it? We know it is 0, 3, 0, right? Because there's no x component, y component is 3, and z component is 0. The first column is the unit vector of xb with respect to coordinate frame A. We know that xb is pointing in the z direction. So the unit vector of xb is 0, 0, 1. What is YB? YB, second column, describes the unit vector YB. So YB is pointing in the minus x direction. So it is 0, minus 1, 0. What is ZB? Here, the third column represents ZB hat, the unit vector. So it is pointing in the minus direction, the negative direction of YA. Therefore, it is 0. Let me see, did I make a mistake somewhere? I think I made a mistake here, right? So YB is minus x. So let me what is happening here? Okay, never mind. Let me do this again. I think we were here. So let me write T. We are interested to find TBA, right? We are interested to find TBA. This is always 0, 0, 0, 1. What is my xb with respect to a, it is in the z direction, 0, 0, 1. What is yb? It is the minus x direction, minus 1, 0, 0. What is zb? Is the minus y direction, 0, minus 1, 0. What is my t? T is 0, 3, 0. Let me quickly check if that's what I got. 0, 0, 1, minus 1, 0, 0, 0, minus 1, 0, 0, 3, 0. Okay, so that is by observation, or you can consider a series of rotations and translations. So imagine, so we want to arrive at coordinate frame B. So imagine there's a coordinate frame V which coincides with coordinate frame A, which means xv and xa is parallel, yv and ya is parallel, zv and za is parallel, and the origin is the same as well. The origins are the same. All right, from here we move to here. All right, to 0, 3, 0, and now it becomes coordinate frame v prime. So we have xv prime, yv prime, and zv prime. So let's obtain the homogeneous transformation matrix, or the pose TV prime A. That means coordinate frame, what is the pose of this with respect to A, or with respect to V, right? So from, you can use once again observation. If you look at, well, if you use observation, then you might as well use observation and solve everything. So maybe the reason why you're doing this is because you don't want to use the observation. So let's look at the formula. So what is the rotation? We want to construct this matrix. What is the rotation? There's no rotation, because as you can see, yv is parallel with ya, and xv prime is parallel with xa, zv prime is parallel with za. So if we look at the rotation matrix, you can choose any of this because there's no rotation, and if you substitute 0, you will get identity matrix. So 3 by 3 here is identity. Why 3 by 3? Because this part is 3 by 3. But this one is the position of this origin with respect to coordinate frame A. And the position here is 0, 3, 0, 0, 3, 0. So there we go. So the next step, or the next motion, is we rotate. As you can see, we rotate about xv prime positive 90 degrees. So yp prime goes here. So we have yp double prime, and z goes here. We have this. So from here, we go here. So let's obtain tv double prime v prime. So this 3 by 3 is rotation matrix, and we see that we have rotated this coordinate frame about xv prime, x-axis, and the angle is positive 90 degrees. So we have to use this one. So cos 90 is 0, minus sine 90 is minus 1, and here sine 90 is 1, and this is 0. And there's no translation, right? The origin of this coordinate frame with respect to this coordinate frame is the same, is 0, 0, 0, right? We do not have translational motion here. So this is t v double prime, t v prime. So from here, we have to perform another motion to obtain our B coordinate frame, which is our problem to be solved. So as you can see, how to obtain this from here, we rotate about ZV double prime axis 90 degrees. So XV prime goes up here, becomes XB, and YV double prime goes down here, becomes YB. And we have to again construct the homogeneous transformation matrix. The last row is always 0, 0, 1. This 3 by 3 is the rotation matrix, and you have to be careful. We have just rotated about the z-axis, therefore we have to refer to this, right? Cos 90 is 0, this 2 is 0, minus sin 90 is minus 1, sin 90 is 1, and the origin of this with respect to this is 0, 0, 0. So what is TBA? Something that we want to find. It is TV prime A multiply TV double prime V prime multiply TB V double prime. You have to make sure the subscript and the superscript is the same. So if you perform this multiplications of the three matrices, you will arrive with this, and you can do this using your calculator. And because we are interested to find PA, so this multiply PB, P tilde B, PB is 0, 1, 0, so 0, 1, 0, and we have to express it in homogeneous coordinate by appending 1 here, and the result is minus 1, 3, 0, 1, but PA is just the first three elements, minus 1, 3, 0. Let's check. Minus 1, 3, 0. So that was correct. Let's move on to the next topic, configuration space. We have so far considered the pose of objects in terms of the position and orientation of a coordinate frame affixed to them. For an arm-type robot, we might affix a coordinate frame to its end effector, while for a mobile robot, we might affix a frame to its body that we call body fixed or body attached frame. So this is, imagine this is a robotic arm, and we might attach a coordinate frame at the end effector. So when the robot and thus the end effector moves, this coordinate frame will move together. And similar with a mobile robot, we may attach a coordinate frame fixed to the robot. So this is sufficient to describe the state of the robot in the familiar 2D or 3D Euclidean space, which is referred to as the task space or operational space, since it is where the robot performs tasks or operates. So before this, we have learned about poses. So a pose, or the position and orientation of this coordinate frame, is enough to determine the state of this robot with respect to our task space. So in this context, the task space can be a room. Well, we won't be using a robot to operate in the entire room. So you can imagine a 1 meter by 1 meter by 1 meter cube, which is part of the room in which we would operate our robot. So that is our task space. When it comes to a mobile robot, if you have a robot vacuum cleaner, so the floor of the entire house can be, which is two-dimensional space, can be our task space. So that is using poses. So once again, so until now we have learned that how to describe relative poses mathematically, and that actually describes the state of our robot or of an object. An alternative way of thinking about this comes from classical mechanics, and it is referred to as the configuration of a system. So rather than talking about the pose of an object, now we'll be talking about the configuration of a system. So both are referring to the state of our robot. The configuration is the smallest set of parameters called generalized coordinates that are required to fully describe the position of every particle in the system. This is not as daunting as it may appear, since in general, a robot comprises one or more rigid elements. In each of these, the particles maintain a constant relative offset to each other. If the system is a train moving along a track, then all the particles comprising the train move together, and we need only a single generalized coordinate q, which is the distance along the track from some datum to describe their location. So what it says is that if we have a train on a piece of land, so that piece of land has x-axis and y-axis, so that piece of land is our task space. First of all, because we want to move from A to B on this land. So this is our task space. And imagine there's a railway or train track. And the configuration of the train can be fully described by a single number, which is the distance along the track. So if we map this track on a straight line, which we will call XC, so 1 here is 1 here, and so on, and the maximum of this track is 100, so we have 100 here. So the configuration of our train can be completely described by only one number, which is by this number. So if I say the configuration of my train is 2, we know that it is here. A robot arm with a fixed base and two rigid links connected by two rotational joints has a configuration that is completely described by two generalized coordinates, the two joint angles Q1 and Q2. So now this is a robot arm with two links and two joints. Imagine this is a joint here, joint 1, joint, and this is joint 2. And the angle exerted by this joint we label as Q1, and the angle given by this joint 2 is Q2, and this is our end effector. So the configuration of this robot arm is simply given by Q1, Q2. And of course, this is an element in a space. So this is Q1, Q2 space. So for example, this can be 45 degrees and this can be 35 degrees, and it's just a point in my two-dimensional space. And of course, you know that Q1 doesn't go from 0 to 360 because there's a limitation here. Maybe in the actual robot, Q1 can be only from 15 degrees to 165 degrees due to the physical limitation of the robot arm. So C is a bounded space in this two-dimensional space. The generalized coordinates, as the name implies, can represent displacement or rotation, as we have seen, and the number of independent generalized coordinates n is known as the number of degrees of freedom of the system. So here the n is 1. So in our simple train system, the degree of freedom is 1. And for this, for our robot arm, since we have two elements here, n equals to 2, and therefore the degree of freedom here is 2. Any configuration of the system is represented by a point in its n-dimensional configuration space, or C space, denoted by this special C, and Q, which is our configuration, is an element in C, in our configuration space. So what does it mean? So this is our configuration space from 0 to 100, and each configuration is just a point, right? So similar to here, my configuration space is this, and I've already told you it has to be bounded. There has to be constraints, limitations on the angle, because our physical robot arm has limitations. Therefore, the angle here doesn't extend from 0 to 360. It has to be limited. So each configuration is just a point in my configuration space. For the train example, C is a subset of R. So R extends from minus infinity to infinity. So C is just from 0 to 100. It's a subset. And for the two-joint robot arm, the generalized coordinates are both angles. Any point in the configuration space can be mapped to a point in the task space. But the inverse is not necessarily true. Okay, so in this case, in our train case or example, the task space is this one, the two-dimensional space, and configuration space is this. So it says here any point from configuration space can be mapped to task space, which is true, right? So 1 here I can map to here, 2 map to here, and so on. 100 maps to here. But any point on my task space not necessarily can be mapped to here. For example, if I take a point here, can I map to configuration space? Yes, right? From here we go here. There's a mapping. There's a mathematical relationship, right? We can always project one point to another point. But if I want to map a point here, can I map this to my configuration space? The answer is no, because you can clearly see it's not possible because the track does not pass through this point. And the same thing with my robot. Perhaps a point, because you can imagine this is my task space and this is the maximum my robot can reach, right? So anything within this circle is my task space. But if I choose a point here which is beyond the reach of my robot, so I cannot map this point to here. Consider again the train moving along its rail or the track. We might be interested to describe the train in terms of its position on a plane, in which case the task space would be tau. Or sorry, the task space, right, t. Or in terms of its latitude and longitude. Okay. We might choose a three-dimensional task space t to account for height changes as the train moves up and down hills, and its orientation changes as it moves around curves. However, in all these cases, the dimension of the task space exceeds the dimension of the configuration space. We know that dimension of t, which is 2, is greater than dimension of c, which is 1. This means the train cannot access all points in the task space. While every point on the rail line can be mapped to the task space, most points on the task space, while every point on the rail, which is this one, can be mapped to the task space, right, from here to here, most points on the task space, for example this one, will not map to a point on the rail line. The train is constrained by its fixed rails to move in a subset of the task space. And similarly, the simple two-joint robot arm can access a subset of points in a plane. So a useful task space might be this one, right? Like I said, within this circle, which is a subset of the two-dimensional space. So this is two-dimensional space, and the task space is just a subset of it. The dimension of the task space is still 2, equal to the configuration space here. This configuration space is also two-dimensional. This means the mapping between task and configuration spaces is bidirectional, but it's not necessarily unique. For this type of robot in general, two different configurations map to a single point in the task space. So what does that mean? So let's say we have a point here, P, on the task space, right? This is my task space. So using the same robot, there are two ways I can get to this point. One is by using Q 45 degrees, 135 degrees, and the other one is by using, the other configuration is 225 degrees and 90 degrees perhaps. So two different configurations map to a single point in the task space. So you can imagine you have 2 points here. This is point 1 and point 2. So they both map to the same configuration space. From here to here and from here to here. It's a mapping. Points in the task space beyond the physical reach of the robot are not mapped to the configuration space. So like I said earlier, a point which is beyond the task space, we cannot find a mapping from here to configuration space. And of course, if we choose a task space with more dimensions, let's say if I choose a 3-dimensional space which is greater than my dimension of the configuration space, the robot will be only able to access points within a subset of that space. Now consider a snake robot arm, which is shown in figure 11. So this is a snake robot which has 20 degrees of freedom with 20 joints. In this case, an infinite number of configurations in a subspace of the 20-dimensional configuration space will map to the same point in task space. This means that in addition to the task of positioning the robots and effector, we can simultaneously perform motion in the configuration space to control the shape of the arm to avoid obstacles in the environment. Such a robot is referred to as over-actuated or redundant. So that means we have more joints than needed. All right. So if we have so let's say if we have a point here, so using the snake robot, so not only we can reach this point, but we can also control the shape of our robot, in infinitely many ways, because it has more joints than required. So the body of a quad rotor, such as shown in figure 12, this is a quad rotor which has 4 rotors. So as shown as this, right? It's a single rigid body whose configuration is completely described by 6 generalized coordinates. So the configuration is given by 6 generalized coordinates. So you can imagine this is Q1, Q2 up to Q6. But this is Q1, Q2, Q3 is the position in a 3-dimensional space. And theta x, theta y, theta z is just the rotations about its coordinate frame. So the rotation about x-axis is theta x, the rotation about z-axis is theta z, and so on. For such a robot, the most logical task space would be equivalent to the configuration space. However, the quad rotor only has 4 actuators, 1, 2, 3, 4, which means it cannot directly access all the points in the configuration space. Hence, its task space. Such a robot is referred to as under-actuated. So the dimension of our configuration space is 6, right? We have 6 quantities here in our configuration space, but the amount of actuators, we only have 4. So we cannot possibly reach or access every single point in our configuration space. So which means if you want your x, y, z, theta x, theta y, theta z to be a specific value of vector, maybe your quad rotor cannot achieve it, given the limitation of the number of actuators. On the other hand, in the previous example, when we looked at our robot arm, in this case, so here the number of joints is 2. So in each joint we have actuators, right? So one actuator here, another actuator here. So 2 actuators, and we have two elements of configuration. So that means the dimension of a configuration is 2. So this is not under-actuated. So for whatever value of Q1 and Q2 within the limitation of the physical system, we can achieve it, right? But in our quad rotor, it's different. For example, if you want x1, x to be 5, y to be 5, theta z to be 5, x 5, y 5, z 5, theta x to be 0 degrees, theta y to be 90 degrees, and theta z to be 30 degrees specifically, most likely your quad rotor will not be able to achieve that, given the 4 actuators. Okay, then that's all for this chapter. I'll see you in the next chapter.